Welcome to Standing for Truth. My name is Donnie, and I am your host for today's show. One of the many ways that we defend the truth of biblical creation here on Standing for Truth is by inviting some really awesome guests onto the program. And today, it is a privilege to have Dr. Jerry Bergman here with me for another presentation, today's presentation specifically on mutations, the so-called driving force of evolutionary change. As most of you know, this is not Dr. Bergman's first time here on the program. He has been here many times in the past, and he has been a huge blessing to this ministry and our audience. If you'd like to check out Jerry's previous presentations with us, please check the description box of this video where I've got all of the relevant links there posted for people to check out. Jerry's done presentations and talks with us on Neanderthals, evidence for creation, God made the universe just for you, C.S. Lewis, which I have Jerry's book on C.S. Lewis behind me, evolutionary blunders. Last week, we did an excellent program that I had a lot of fun with, demolishing evidence for human evolution. And so I think within that hour and a half, we basically tackled nearly every line of evidence for evolution. And so if you haven't yet seen that one, I highly recommend checking it out. Now, before I hand it over to my guest for his presentation tonight, I do want to give him a proper introduction. And so Dr. Jerry Bergman has taught biology, genetics, chemistry, biochemistry, anthropology, geology, and microbiology for over 40 years at several colleges and universities, including Bowling Green State University, Medical College of Ohio, where he was a research associate in experimental pathology, and the University of Toledo. He is a graduate of the Medical College of Ohio, Wayne State University in Detroit, the University of Toledo, and Bowling Green State University. He has over 1,300 publications in 12 languages and 40 books and monographs. His books and textbooks that include chapters that he authored are in over 1,800 college libraries in 27 countries. So far, over 80,000 copies of the 60 books and monographs that he has authored or co-authored are in print. I have several of Dr. Bergman's books with me. I try my best to keep up on all of the articles that he puts out on his website. I highly recommend checking out those articles as well as his books. Please, again, check the description box of this program, and you'll find a link to Jerry's website. Okay, so with that, Jerry, it's great to have you back with me for another presentation. I always enjoy your presentations, very informative. And so how are you today? And I'll just give you the floor.
I'm doing okay, just anxious to give this presentation. I've given this many times, and I always look for critical feedback, and I just haven't gotten any from this. People really can't dispute most of what I say because it's well documented. And this deals with the fact that evolution did not and could not ever happen. Well, what do the leading evolutionists teach? Well, Steve Hawking, who died a few years ago, says science has shown religion was wrong. In his words, science provides a better and more consistent answers, but people will always cling to religion because it gives comfort and they do not understand science. Well, I have a problem with that statement, but it illustrates what so many evolutionists believe. And further, he said, well, how do we explain the natural world? Well, he says the Big Bang explains the origin of space, matter, energy, and time from nothing. In the Big Bang, he says, quote, you can get a whole universe for free because the fantastically enormous universe of space and energy materialized out of nothing from the Big Bang. This, I would say, is magic. Materialized out of nothing. We have a choice, basically, of the options that are available, and materialized out of nothing just does not appeal to my scientific mind. Then he says, thus the universe itself, in all its mind-boggling vastness and complexity, could simply have popped into existence without violating the known laws of nature. We do, he adds, we do not need a God to set it up so that the Big Bang could bang. Mysticism. And I like to look at evidence. Well, what I've done in my presentation is looking at empirical evidence, which if you work in a lab or do research in this area, you can find indeed the conclusions I bring out are valid. And Dawkins added a page later, he prefers, and this is really important, he prefers to think that everything can be explained by the laws of nature, but he never attempts to explain the origin and what sustains these laws, the origin of these laws and what sustains them. And so in any ways, that's his worldview. And he also attempts to show how life was created without a God. Somehow, and you'll notice the iffy terms he uses, somehow some atoms came to be arranged in the form of molecules of DNA. As DNA reproduced itself, there would have been random errors, many of which would have been harmful, and a few errors would have been favorable to the survival of the species. These would have been chosen by Darwinian natural selection. And again, when you read what he has to say, it just is so much mystery, so much, well, it just happened, popped into existence. The other side is, I will explain, research proves evolution is true, but it is going the wrong way. And evolution, I'll define it, and this is the title of a leading biology textbook. Evolution is from molecules to man. First of all, the problem is not survival of the fittest. That's pretty obvious. That's like saying rich men have lots of money. But the arrival of the fittest has always been the problem. Darwin realized this was the problem, and this is still the main problem today. And when we look at the various drawings which show evolution, basically we're looking at beginning with molecules, or in this case, a cellular, single-celled animal to mankind. This is an interesting chart because this was accepted a few decades ago, and as our evolutionary ancestor includes a, believe it or not, a kangaroo. So we've come, I guess, a long time since that. Okay, the primary basis of macroevolution is mutations. And therefore, to produce variation that can be selected by natural selection, we have to change the protein that is done by changing the code of DNA, because DNA produces the protein, and therefore changing the protein affects the phenotype, and as a result, it affects the ability of the organism to survive. And Ernst Mayr, who is a leading evolutionary biologist, he just died a few years ago, professor at Harvard University, he said, ultimately, all variation is due to mutation. Theodoros Dobzhansky, another well-known leading evolutionist, said mutation is the only source of the raw materials and hence of evolution. So if you do much reading in this area, you realize that they depend almost totally upon mutations for the basic changes that allows evolution to occur. And the importance of this, I present the same picture in several of my presentations because it is so amazing. This was Professor Hermann Mueller, and Dr. Mueller basically discovered that if you put fruit flies under an X-ray machine, zap them, it causes mutations. And as a result of this discovery, he was given the Nobel Prize because he found ways of increasing the mutation level and thus of increasing evolution. Well, now we know unequivocally, and this is the work I did at the medical school, we know unequivocally that mutations don't speed up evolution. Mutations speed up decay. They speed up disease. They cause disease, cancer. That's what we worked on, was cancer, which is basically a disease of mutations. And Mueller, his presentation he gave, he said he discovered X-rays, and this is part of his Nobel Prize. X-rays can increase the mutation rate in living organisms by as much as 100 times. So Mueller reasoned, that he could drastically speed up evolution by creating mutations by X-rays. And he said, not only is this accumulation of many rare, mainly tiny changes, the chief means of artificial animal and plant improvement, but it is a natural selection or natural evolution, he uses the term here, has occurred, guided by natural selection. Thus, the Darwinian theory becomes implemented. And this, again, was part of his Nobel lecture that he gave when he was given the most prestigious honor in science, and that is the Nobel lecture. Now, let's look at some illustrations of this. Richard Dawkins, probably one of the leading evolutionary biologists today. Professor, he's retired now, but he was a professor at Oxford University, and he explained evolution this way. You type in a bunch of random letters in a computer, and then you program the computer, which to him is likening it to natural selection. You program the computer to select certain letters. In this case, he wants to get me thinks it is like a weasel. And therefore, W, which is what he typed in by random, changes would occur until an M was produced, the first letter, that, M would be saved. He did that until after 44 changes, he ended up with his goal, me thinks it is like a weasel. And creationists like to look at this because this is an empirical explanation as to how evolution occurs. The problem is, though, he's got the end of the sentence, in this case, a sentence, the end of the sentence is programmed into the machine to select random changes to end up with that sentence. And of course, we're talking now about intelligent design. We're not talking about random variations in the genes, which eventually evolution selects. Now, when we look at mutations, there is a number of problems with this. Number one, Dawkins' idea was all the letters could be randomly changed until we got the right ones, which fits his goal. The problem is that there are in all studies shown hotspots. Hotspots, and this is very important because in cancer, we look for hotspots because that tells us something about the cause of cancer and therefore the treatment. And when we examine the hotspots, we find that of the genome, and you can see this, there's the red lines show how common mutations are. And you can see there's a few scattered mutations, a few cases where there are 2, one case where there's 3, and then a vast majority, like I think around 90%, are in this one area, which is base pair 199 in this gene. So we're not going to get the changes that Dawkins expected because we end up with hotspots. Okay, in one study, only 2 mutations accounted for 94.4% of all mutations out of the 319 they identified. And these hotspots are areas that are weak or in a certain place in the gene where they're more prone to being affected by mutations. So if you apply this to Dawkins' illustration, what we have is a few changes. Those changes are in bold here in my illustration. The top line, you can see a T, and that changes to a Y. That changes back to a T. That changes to a K. That changes to an M. We will never, no matter how many millions of changes we go through because of hotspots, we will never end up with me thinks it is like a weasel. It's not going to happen because of these hotspots. And again, this is very important in studying cancer. Very important in discovering genes because we often know where the mutation is, and therefore we know something about the cancer, what causes it, and how to treat it, ideally. And are beneficial mutations common? That is an important area because they claim we're talking about presentation of beneficial mutations. Well, I'll give you a few examples. Did a literature search, and I found that of the total mutations, about 500,000 I located in the various literature abstracts. Out of those, there was 186 that were claimed to be beneficial. So I looked at all of those that claimed to be beneficial, which is about 0.04%, and I found all of those were beneficial in minor ways, or they're beneficial because they turned something off, allowing something else to be expressed. It's like a lid on a jar is locked. So you have a change, a mutation, that allows the lid to be opened, and it doesn't improve it, it just allows you to get at the information, which in this case, the food you're after. And there are some positive examples of beneficial mutations, but if you think about it, many of them are beneficial, well, in this case, for us. And a good example is seedless fruit. That's it, mutation, which is beneficial, but it's not beneficial for the fruit because for the fruit, it's lethal. For us, it's beneficial because you don't have to worry about eating the orange and spitting out seeds. So it's beneficial in this case for us in a very limited situation, but not beneficial for the plant in this case. And this is one of my favorite examples because I was in Sweden when I talked about this, and students in the university said, hey, Belgian blue cattle was discovered right here in Sweden. And I was kind of surprised, and they were surprised that I mentioned this. But it was very beneficial, this mutation, to beef farmers because it had more muscle, the meat was more tender, and low in fat. So if you think about it, this was, again, for us, very beneficial. And it would have been beneficial for the farmer, except, well, a problem developed, which I'll talk about in a minute. And that's what the cow looks like. They were a very meaty cow, the Arnold Schwarzenegger of the cow world. And there they are, nice and strong. And of course, it sounds, well, so what? I mean, it may not look as handsome as many cows or other similar animals, but on the other hand, it's got a lot of muscle, ideal for the farmer. And the problem is, though, several. One, it reduces the cow's fertility. And two, even though it produces a beneficial effect for farmers and consumers, the result of what happened was information loss. So the mutation was the result of information loss. Specifically, and when I was in Sweden, I talked about this, they recognized it. Specifically, there are breaks which stop muscle development when it gets to a certain point. These breaks were broken, and as a result, muscle development went beyond what it should have. And therefore, that's why they had so much muscle and looked like the Arnold Schwarzenegger of the cow world, the animal world. And this occurs, by the way, in other animals as well. The problem is, though, they had so many health problems with these cattle, they gave up. It did not become popular. There were too many issues. Specifically, we know that this is a result of a deletion for an 11 base pair coding region in a homologous deletion. And therefore, something was broken, which in this case didn't turn out to be beneficial either. The classic example of lost mutation was discovered in 1791 by Seth Wright. And I mention this because Darwin mentioned this. He said this was a new species occurs in one generation. And the males were normal, except they had very short, bent legs, and they resembled dachshund dogs. And the advantage was they couldn't jump high fences. You know, sheep, they wander around. They're not very contained in one area. They're not herd animals so much. They do their own thing. And as a result, you have to have fences or you have to have dogs or something to keep them together. And these sheep, though, could not jump high fences. So thus you put in smaller, shorter fences, save money if you had these Ancon sheep because they couldn't even jump low-level fences. And so they thought, well, this is a new breed. Turns out to be beneficial, again, though, for us, not for the sheep. And there you can see in a textbook, I noticed that this sheep is featured in textbooks up to the late 50s and some in the early 60s. And this was an example in the biology textbook of beneficial mutation. And they were saying, beneficial mutations, here you go. Here's a good example. And this was the example they used over and over. Now we know that this is not very helpful for the animal. In fact, it's caused by a lethal deformity called achondroplasia. So we had achondroplasia animals. And this breed, though, went extinct in spite of all efforts to save it. And there you can see a normal sheep on this one side here. And achondroplasia in humans, there's a young man who happens to be an actor who has achondroplasia. He has a normal part of his body from his waist up, but from the waist down, his legs don't grow as long as they should because of achondroplasia. And this was the same problem that the sheep were experiencing. I did give this presentation at Ohio State University a few years ago, and one of the professors in the audience had a hard time with what I was saying. And he said, I will find an example of a beneficial mutation. I said, I really appreciate that if you would try. And after a few months, I hadn't heard from him. So I emailed him and said, hey, You said you'd find an example. I want evidence against my position. I want to look at this evidence because I may be wrong. And he says, okay. He sent me this information about this man who had 6 fingers. And that, he said, really helped the man because he could climb trees faster than most of us because of those 6 fingers. And there we have an x-ray, and you can see 6 normal fingers, which look fine. And then I thought about this, and I was aware of this because of the Amish. And the Amish have this mutations common. And I was aware that this guy has a good example of a pretty well-developed normal hand, but most are not. In fact, and there you can see another example of a mutation that turned out okay, but on the other side, you can see what is normally true is we have a mess. And typically, when we have these extra mutations, these extra fingers from mutations, typically end up losing a lot of fingers because 98% of the time, it is not helpful, it is harmful to the person. And we have a lot of examples of these, especially among the Amish, because they intermarry their relatives, and therefore this mutation tends to be common. And a few other examples you can see, the fusion of the fingers did not occur, and so this person has, instead of 5, he has 1 less. And what happens here is that the fingers actually form as a set, so you look like an animal's paw, a dog's foot. But what happens is that the separation occurs later when the the bone is larger and they're stronger. And in this case, the separation, which they call apoptosis, the separation didn't occur. And as a result, the separation didn't occur, and therefore the 2 fingers look like all the fingers would have looked like in the womb of the child. And so again, this is a result of a mutation, which was not beneficial. Here we have a child born with a complete 3rd arm. Now that would really be useful. I would find that very useful working around the house. I could work on my computer, and I could also do something, listen to the telephone or do something else. But it turned out both hands in this case were non-functional and they had to be removed. So instead of a helpful mutation, this turned out to be a loss. And occasionally you get this in animals. This is, by the way, what they call stuttering mutations, where a control system, instead of producing 1, 2, 3, 4, 5, 6 legs and stopping, there's a mutation which causes it to continue to produce more legs. In this case, this animal had 1, 2, 3, 4, 5, 6, 7 legs, and it couldn't walk. Fortunately, the farmer was able to display him, and he got some money from people who came in to watch his animal try to walk around, which he couldn't, of course. And so he could take care of this animal, even though normally in life you would not want to take care of this animal, but he made some money off of it, so he was pretty happy. So this is another example of a mutation. And there are many, many examples of mutations. Again, the vast majority, not every one, but the vast majority are harmful. Here is a tortoise, a turtle, which has 2 heads. And I'm told that's a problem because one head wants to go in one direction, the other head wants to go in the other direction, and we end up with a schizophrenic, poor turtle. Big problem. A child here you can see had 2 faces. This was twins, which didn't separate properly. And we end up with a child that has 2 faces. And again, a few other examples. We have a child who had a twin, and the twin grew as part of the child's body, caused by a mutation. And as a result, it didn't grow up. Neither children in this case grew up normally. Then we have some mutations like a Hertzu child. And this person here grew up with this condition and wasn't an evolutionary throwback because they thought it was a disease which causes head hair to spread throughout the entire body. And that's a problem in our society. And here's another case of a mutation. This child was not an Einstein, but the brain grew so large, it crushed the tissue, and as a result, the child died. And you can see the child is not very happy there. And here's another case. This was in Russia, where they were trying to evaluate the effects of radiation from atomic bombs. So they lined up a bunch of the townspeople, women who were pregnant primarily, and they lined them up and they covered their eyes, so they didn't want to blind them. They covered their eyes, they were pregnant, they blew off the bomb, and then they wanted to see what effect the radiation from the bomb had on the fetus that the women were carrying. And they were hoping back then, of course, they accepted the idea that mutations cause evolution. And back then they were hoping to get a couple geniuses, a couple, children who had exceptional abilities in some area, or at least were better in some way. And what they found was a lot of the babies were born, like this one was, deformed. And there's a museum nearby which displays a lot of these, and I selected a couple of these which illustrate what happens. So again, what do we see going on? And most people know this. Most people know radiation causes mutations. But yet they will, with a straight face, accept the idea, well, how does evolution occur? It works by mutations. And here's two more examples of Cyclops. And of course, both of these were born dead. And there are many other examples. Now, one example of beneficial mutation, which is often touted, is resistance to antibiotics. And in this case, we have the ribosome. The ribosome is a jig which facilitates in translating the DNA code to proteins. And in this case, streptomycin fits inside of the jig and therefore stops the ribosome from working. It turns it off. And as a result, the person, the bacteria in this case, with streptomycin, does not, the mutations cause the problem. In this case, we're looking at bacteria. And of course, it occurs in humans as well. But in this case, we're looking at bacteria. And therefore, it turns off the ribosome. And as a result, the ribosome is controlled or affected by the streptomycin. Now, as a result of the mutation, okay, you can see mutation in the ribosome here. The streptomycin cannot fit in the slot. Therefore, it cannot turn off the ribosome. Therefore, it no longer is effective in killing bacteria. And there are many examples of this, but this is probably the most well-known. So streptomycin turns off the ribosome. As a result, the bacteria cannot reproduce. But if you have a mutation in the spot where the streptomycin docks, as a result, we end up with the streptomycin doesn't work. And as a result, we end up with a bacteria which is resistant to streptomycin. But now that ribosome control center is important for a reason. And as a result, when the mutation occurs, the bacteria is not healthier. Yeah, it may resist streptomycin, but it's not a more evolved, it's not a better, it's not an improved bacteria. It is a less effective bacteria. And this is probably my favorite example where you have HIV resistance. And they discovered certain people, they can be exposed to HIV and never come down with the infection. And now we know that there are two sites which the virus has to fit like a key into and therefore get inside the cell. And it's like you have to get inside a room, you have two keys. To get inside the room, you have to have both keys. And then you have to open the door and go in the room. Well, what happens is that the cell, in this case, a macrophage, the CCR5 receptor is damaged, it's broken because of mutation. And as a result, it doesn't dock on the surface. And as a result, the HIV cannot bind with a CD4 receptor. And as a result, it cannot get into the cell. And as a result, you have a person here who is resistant to HIV. And at first, when this was discovered, they thought, boy, this is amazing. This is really interesting. Well, as you may expect, when that CCR5 receptor is non-functional, what happens is we end up with a person who's more prone to other diseases like leukemia. And therefore, it may be beneficial in one case, but it's harmful in other cases. And two issues that I'm aware of is immune system is less functional, and they end up with prone to developing liver cancer. Shermer estimates, Michael Shermer, who was on his way to become a seminarian, to become a pastor, pardon me, was exposed to evolution. And guess what happened? He became an evolutionist and now is very active. He's head of one of the larger atheist groups. And he said, to evolve humans, trillions of distinct mutations are required. And presumably, each modification requires many mutations. And so therefore, well, he said many. How do we get humans? How do we evolve? Through trillions of distinct modifications. Well, we know that 99.99% are not beneficial. They're harmful. Some are near neutral, but those add up and cause a problem. It's like a small problem in your car, and you can still drive it. And after 3 or 4 other problems develop, you end up with that damage adding up, and then you can't drive the car. So likewise, what happens with people is, even with so-called non-dangerous mutations, they add up, they cause problems, they cause specifically what they call mutational meltdown. And as a result, this trillions of distinct modifications is never going to get us evolution, as Shermer estimates, but it will get us, indeed, mutational meltdown. And most mutations, though, are near neutral. That means they're not selected against, but they accumulate. And the best example by far of the accumulation of near neutral mutations is aging. That's what causes us to age. My aunt, when she died, and I don't know that she was ever in hospital. So when she died, I asked the doctor, what happened? What did she die of? And he said, well, she didn't die of anything. And I thought, no, wait a minute. She died of something. You don't die of no reason. There's some reason she died. And he said, well, sit down. I'll explain to you. She was, I think, 92. Her liver wasn't working as well as it should. Her kidneys didn't work as well as they should. Her veins and arteries were not working as well as they should. She didn't die of any one thing. She died of everything. She had a lot of things that were not damaging or not deleterious separately, but as a set, caused her to die. And so what we do is, and this is not uncommon, what we do is we just, on the birth certificate, died of myocardial infarction. I mean, that's, in the end, that's what happened. Her heart stopped. That's what happened in the end. And so rather than list all these things, well, her kidneys were only 70% effective or 60% effective. You don't list all that. You don't have room on the death certificate. So you just say cause of death, myocardial infarction, end of story. And doctors know when they see that there probably was a lot of things wrong. And not just, of course, the brain, but sight, smell, and hearing, and stomach, intestines, everything was wrong. So founder mutations, these are disease-causing mutations that are not eliminated by natural selection because they're not lethal. And these persist in the population, can become widespread. And the most famous example, of course, is sickle cell anemia. And the person who suffered the first mutation is called the founder. That's called a founder mutation. And that's often lost in history. But sometimes we can determine who was the founder mutation. And we can trace everybody who had that mutation back to that original person who had the founder mutation. And they're most likely to persist if they're recessive. So if you have a normal and a recessive, the normal will work fine. Recessive doesn't work, but you've got the normal, so you're okay. So it only causes a problem when you have two recessive. And that, of course, would be sickle cell anemia is the best example, and malaria would be another example where you come down. And founder mutations contribute to disease. Sickle cell anemia, I think there are 5 founders. It's hard to know with that because we're going way, way back, but probably 5 founders exist. Hemochromatosis is another example. Factor V Leiden is another example. Many others exist as well. And so these add up, and in time they cause extinction of the organism. And this is why, these are reasons why evolution is true, but it's going backward. Pleiotropy is another issue, and that is where one gene influences many phenotypical traits. So you have one mutation and it causes many different effects. And that is an issue which we have to look at. One area when we diagram the body's genetic pathways, we can see here charts that look like this. It's a mess. If any one of these areas is blocked, you could have a health problem. And since that probably looks like a mess in front of you, of course, it's not a mess. This was all painstakingly developed by scientists through years, but we can see the mutations, if they affect one area, how they affect other areas, because the lines show us one gene affects these other areas. And another example you can see here, D-fructose. And we can see then this is the effects here on this way and the effects going this way. And so we can see if we have a mutation, say over here in the ketohexokinase, then we end up with problems in production of D-fructose and other problems along the line. So we can see that the body is a vast network of coding information which affects many, many parts of the body. And we can see damage of one can have other effects. The interactome is where we're trying to understand how genes and thus proteins interact. And these right here are the proteins. And we have a line. This protein here, for example, affects all these proteins here and all these proteins where you can see the lines. So you look at any one of these, especially the one with all the lines coming from there, you can see that affects a lot of other proteins. And the reason that we don't have more lines is because we're still learning. We're still filling in what they call this interactome. And when we fill it all in, my guess is you're going to have a massive lines. Be hard to follow anything. So we're talking about enormous complexity in the Bible, I said the word Bible, the Bible as well, but other means of complexity in the body. And this right here, you can see a message when it's carried from the outside. This is the outside of the cell. When it's carried to the center of the cell, you can see all of the proteins it has to go through. It's like before I can see the president, I have to go through 35 different lines, all which have to approve my coming in order to see the president. If any one of them along the line does not accept my invitation, I'm blocked. I don't get to see the president. And now we have another problem which is developed in understanding the relationship between genes. And that is we have at the top here a protein coding gene right here. Starts over here, ends up over here. But when we examine that, we see within that protein coding gene, there are other genes inside, outside, some partly inside and partly outside. But that gene, which is partly inside and partly outside, also in that gene area is another gene. And a good example of that is, of course, we have words, long words, and in those words, we have other words embedded in the other words. And many examples of that I used to play example out like peanuts. From peanuts, how many words can you get from peanuts? And I think the most somebody ever got was like 35 or something like that. But anyways, so now we know 94% of human genes generate more than one product. So when we have damage here, we may end up with changes elsewhere. And this is a problem of mutations. So you have a mutation that occurs here, and it may affect something, producing a positive effect, but it may also affect many other genes, which may produce a negative effect. So we have the inevitable unintended consequences. And that is especially true with mutations. And so if you are going to base humanity as a result of lots of mutations, there's no way you're going to have trillions or even a dozen mutations without causing other deleterious effects, thanks to the example of Pleiotropy and the description of how the genome works. Isoforms, these are when their gene is spliced. One gene, a DSCAM gene, for example, and that can be spliced in 95 different ways. So you end up with 38,000 possible isoforms from this one gene. And what that means is that you have one gene that changes, you could be changing many other genes. Most of them, or many at least, are going to have deleterious conflicts. So you can see from what we know, and this is all well established, any biochemistry book, any genetics book will explain all this and give many more examples than I've given. So the information is there showing indeed that mutations will never bring us to humans or any other animal, period. And so in the more complex system, the more mutations are possible. There are 5,000 genetic diseases in humans. A quarter hit the nervous system. And that's why so many mutations affect the nervous system. And that's because the nervous system is the most complex system in the body. An assembly, this is getting into another PowerPoint, so I'll go through this quickly. In order for this bacterial flagellum to work, you have to be able to have all of these up. Phone. Disadvantage of cell phones, it interrupts you at the wrong time. But anyways, for this thing to work, you have to have all these parts. And that's another PowerPoint. And a good reference, due to contamination of the genome by very slightly deleterious mutations, why have we not died 100 times over? And this, by the way, was in a biochemistry book that I used to teach from. And this executive, a Russian scientist, wondered, why don't we die over 100 times over? Because we know the harm that deleterious mutations cause. And aging, we talked about that as well. Conclusion, at its core, macroevolution is production of new information by mutations, and mutations cannot provide the source of genetic variation needed for selection to occur. And that's the end of my PowerPoint.
Jerry, I appreciate that presentation, as always, very informative. And I really appreciated how technical that was, actually. I think you did a thorough job refuting all of the evolutionists' favorite so-called examples of beneficial mutations. And we've had some great feedback from the audience. And so I think I'll just kind of get right into some of these questions, Dr. Bergman. Okay. And so here's the first question. And you showed some examples of this in your presentation, and how even with gene duplications, you're looking at that which is deleterious and disease causing. But so the question is this, I've got it up on screen, and it is, can gene duplications followed by beneficial mutations? And if I'm not mistaken, evolutionists call this neo-functionalization. So basically, they'll argue that a region of the genome or a gene can be duplicated, and that duplicated region can then be subject to beneficial mutation accumulation, which would evolve a novel gene according to their model. And so do you believe that this is the case? And is this the kind of variation necessary for uphill evolution?
Yeah, this is one argument that has been put forth. It's problematic in a number of ways. Number one is the assumption is that you have a duplication, and the duplication does not cause a problem. The fact is, duplications often cause problems, and there are a number of diseases which are the result of duplications. And another problem is that you assume that you have duplication, one will sustain mutations, the other won't. Well, mutations are likely in both the genes, both the original and the copy. Another argument is, well, one can continue doing the function, and the other then can accumulate mutations and evolve into another gene. But it's not going to be useful until it evolves into that other gene. And then now you might get some minor changes, which might be beneficial. So you can't say duplication of genes is never helpful, but I'm not aware of a single documented example where mutations are indeed helpful. But this method is helpful. Duplicated genes are helpful. And so and you might be able to find some, but my guess is if that occurs, it's not very important at all in producing genetic variety.
Right. And wouldn't logic dictate that if you get a region of the genome that's so let's say we get a gene duplication, now we basically have a useless duplicated gene. And eventually, according to the evolutionists, that has to evolve some type of novelty. But leading up to those beneficial mutations that would accumulate, the gene's useless. So wouldn't natural selection just rid the genome of that duplicated gene? If it's not, it'd be wasteful, I guess is my point.
Yeah, and I would think the proofreading, which is an important system that all cells have, the proofreading basically would go through there and say, hey, what's this extra gene for? There's a problem, so we'd remove it. Especially if the duplicated gene had some mutations. Then it may eliminate it, or it may basically try to fix the mutations and end up with a functional gene. So yeah, that's not really argued by very many evolutionists. They put forth that idea and it didn't last very long. So
Right. If I were to take a book, that I have, and I were to copy it out 10 times, do I really have anything that's truly novel? I mean, I now have 10 copies of a book that I already own. And then if you start adding typographical errors into your duplicated books, aren't you now just um, getting more degraded versions of the original book? If you start adding spelling mistakes into a duplicated gene, it seems to be increasing deleterious mutational load rather than making things better.
Well, that's true. And the system that duplicates genes is, in most cases, designed to duplicate genes for a reason. And so if genes are duplicated that doesn't have that system of control, probably we're not talking about a positive change. We're talking about probably a negative change. And so and some genes do duplicate, and we know that they do that automatically. And therefore, some diseases are a result of so many duplications. It's beneficial. Beyond a certain point, it is not beneficial. Like Duchenne's muscular dystrophy, I think, is one example. Another, probably the best example, is Huntington's disease.
Right.
And therefore, that is a good example.
Is that disease due to just a single point mutation?
No, it's due to Huntington's disease is due to a increase in the certain level of control genes. Beyond a certain point, it's a problem.
Okay.
And you have a loss of the ability to control duplications in Huntington's disease. And that's a good example of disease. We know the founder.
Right.
We know where that came from. And when they were researching this, they found a bunch of people in South America had the disease. And they thought, that blows their founder theory. Well, they went to South America to do the research. They found that disease came from a person from the original area to South America, married, and then had children and grandchildren, and children and grandchildren are all results of the original founder that came from another country, another part of the world. I think it came from Europe.
Is that therefore an example of a disease that is strictly genetic related? Basically through inheritance, if a family member has it?
Yeah, technically all diseases are genetically related. All diseases are a result of mutations. When you have an injury due to an accident, well, that's not a disease. And so your disease you're talking about, and of course you can have other diseases which may not be directly caused by mutations, but most diseases in the long run are caused by mutations, except those caused by pathogens, of course.
Right. I guess what I mean is with Huntington's disease, if you inherit that specific mutation that causes that disease from a family member, let's say, versus maybe certain cancers that might be more environment, might be if you're subject to carcinogens and things like that. It seems like the Huntington's mutation is what directly causes that disease. And so if you don't have that mutation in your family, then it's unlikely to come about.
Very unlikely to have Huntington's disease, yeah. And they can they trace pretty much everybody who has it. And of course, they have to test because you don't know until you're 20, 30, 40, 50. So if it's in the family, then you know you have a certain chance of having a disease. But that's not, fortunately for most of us, that's not a concern. Oh, what you mentioned before, cancer, you're talking about somatic mutation.
Right.
The cells. Now you can have mutations in the germ cell, and that can be passed on. And a good example is the breast cancer BRCA1 mutation, which doesn't show up until you're 30, I guess, 35. And therefore they have to do testing to find out whether you have it. And that's a controversial area, but you'll produce 10 zygotes and they'll check to see the 5 that don't have the mutation. And then of course it's only in women. And then of course you implant that one in the womb, and therefore you destroy, I guess, the others, which is controversial among Christians because you're destroying 10 viable zygotes and you're destroying 9 of them, which is a concern. 60 Minutes did a film on that, and they really did a good job. They did have a Christian family who were concerned about that, and they're very sensitive to that approach and went into detail about why the woman selected the approach that she did. and how difficult that was. But anyways, that's another podcast. I lost you.
Jerry, sorry, I was on mute.
Oh, okay.
Yeah, don't worry. That's my end. So I was pointing out that, firstly, I appreciate your insight on those specific points. But one aspect of your presentation that I really appreciated is how you went through the so-called best examples of beneficial mutations, including HIV resistance, and you went through antibiotic resistance, sickle cell anemia, so on and so forth. And what I've discovered, at least from the evolutionist side, is they base beneficial mutations almost exclusively, they identify them almost exclusively through their phenotype, which you talked about in your presentation, right? The physical characteristics of an organism. And they only pay very little attention to the overall genotypic effect on the actual genetic systems. And so I like how you broke down each example and showed how on the genotype, these examples are actually due to the breaking down of pre-existing systems. They're essentially functionally compromising to organisms rather than being a true benefit. Can you speak to that a little bit, Jerry, how important it is to look to the genotype to see what's really going on with this so-called beneficial mutation?
Yeah, it's a good point because, of course, you get some mutations which do cause a positive result in the phenotype, the body that you can see. But some of these mutations, and many of these mutations, are problematic. You can't see what the problems they cause internally. So you may have certain benefits that are physical outside of the body, but on the inside of the heart, you may have negative results from the mutation. And so that's why when you look at mutations, you have to look not only at the phenotype, but also the genotype and the effect of the body organs themselves. And often we don't do that. And I gave a few common examples, and there are many other examples as well.
And I would recommend that everybody shares this presentation around, because you really did touch on many of what I've seen the evolutionists, even informed evolutionists, utilize as examples of beneficial mutations. I've written notes based on your presentation, and I've also got a few of them listed. And so I found your points on the HIV resistance to be fantastic, because I've seen that one utilized as one of the better examples of a beneficial mutation. But with what you're saying here, when we look to the phenotype and the genotype, and Jerry, correct me if I'm wrong, you were explaining that basically we have a few people in the world that are resistant to HIV, but they actually have a mutation in the gene that makes the CCR5 mutation.
Right.
And so now they no longer have it on their T cell, which means that HIV virus cannot bind to that T cell. So on a genotypic level, isn't that an example of a pre-existing protein basically being knocked out or degraded in order for this advantage to come about?
Well, right. You're talking about damage, and it's like I steal the key to your house, and in the days ensuing from that, you end up with some broken metal which end up in your key slope, and therefore when I come out of your house to steal your valuable stuff inside your house, all your good books, my key doesn't work anymore. So I can't get in, but you can't get in either, of course. So you have to change a lot, and therefore, that change may keep me out because I have a key, but I shouldn't get in. And therefore, this is the same thing that happens with the cell, of course. A lot of people think viruses just kind of float around and go inside of cells, but viruses have to have the key to get inside the cells, and they can't get inside of any cell unless they have the key. And that key depends upon the cell, and that's why viruses can affect certain cells, but not other cells, because they don't have the key to other cells. And that's why some viruses don't cause any problems with us. In fact, the vast majority don't cause any problems with us because they don't have the keys to get into any of our cells. And so therefore they are non-consequential in affecting us. So therefore they can't get in, they can't reproduce, and therefore we're not going to carry that virus. But the viruses, on the other hand, may infect other animals, which their keys do fit in the cells of other animals.
Wow, that's a great response. You're an encyclopedia of information, Dr. Bergman. So many good points. So basically, if I were to cut off my feet, I can't get athlete's foot.
Yeah.
But it's degrading. You know, I'm losing pre-existing systems. So even in this example of HIV resistance, and I'm just so glad that you refuted it, Jerry, because we've seen this pop up. This mutation, it's not telling us where the gene came from. It's not telling us how these systems came about. It's a pre-existing protein that's being knocked out, and overall it's reductive. It's functionally compromising to the organisms that experience it.
Right. Yeah.
Can you speak to the first one a little bit? So on the screen, I've got sickle cell anemia, and I find this one funny because I feel like it's been refuted for 30 years. You know, it's on the genotypic level. Is it not yes, on the phenotype, people with sickle cell anemia, it guards them from getting malaria. So that seems all good on a phenotypic level.
One defective gene. They have to have both defective genes to end up with sickle cell anemia. So if it has one defective gene, they have certain protection against certain problems, malaria specifically, as a result of that one gene. And so you have a benefit with one gene, but with two genes, of course, you don't. Now, the problem here, of course, is intermarriage. When you have your marriage relatives who have that, then you end up with children that have two damaged genes. But if you have one damaged gene and spread that on, that's not a problem. Yeah, this is often an example that's used over and over again. And the reason is that when you have the two genes, or even one gene, of course, damaged, then the malaria can't live inside the cell. And so therefore the cell is not healthy, and therefore the malaria can't live inside the cell. And therefore, in essence, you cannot get contact with malaria because of the damaged cells that you have. And that's the difference. Yeah, there's been whole books written about this. So
right. Well, and you've written about it extensively too, Dr. Bergman. So I look at it like we have this Mount Improbable, basically, for the evolutionists, and you're trying to climb up that mountain, but all you ever do is take steps downward. And right. So how are you ever going to climb that mountain if you're never really taking a step upward? And even if you were to take one step upward at some point, but then another 10 steps downward, you're going to continuously decline. You're never actually going to get to your destination. Isn't that right, Jerry?
Very true. And the problem you have is that there are some reasonable cases like sickle cell anemia, which do support to some degree the evolutionists. The problem is you need thousands of these cases. It's like I find one car that works well, therefore, all the cars must work well. I go out in a parking lot, and the first car I see, I start it up and no problem. So I say, well, they go up in the parking lot and you can start up all the cars and drive them all away. Well, because you had one that you can start doesn't mean the others. Now, it may be you can start the others, but it's not proof that you've got your point made. And so this one example they use, that's fine, but we need thousands of examples to get humans. And the one or two examples that even if they are perfect, are not what we need. We need many, many examples.
Right. And it seems like even in every case where on the surface level, it looks like, okay, maybe this is something that's truly novel and not deleterious in any way. It seems like based on your work and your presentation, again, when you examine it, when you look under the hood, I like to say, when you examine it on a genotypic level, it's still reductive. It's pre-existing systems being knocked out, pre-existing proteins being damaged. And so can we say that those are truly beneficial in your opinion, or Jerry, or how should we approach those kinds of mutations?
Well, they're sometimes are beneficial in very narrow situations.
Okay.
And we can't have a couple examples that are beneficial in narrow situations. We have to have, according to Shermer, trillions of mutations, all that are, or most that are eventually beneficial. And so you're not going to prove a point by even a couple of good examples. You have to prove the point by many, many examples. You have to produce from the goo to you by way of the zoo.
Right.
And it takes more than just a couple of mutations, even if they are beneficial.
Right. To take your fish to fishermen, you're going to have to accumulate truly beneficial mutations that can counterbalance. And this is what I really appreciated about your presentation, how you pointed out that the vast majority of mutations are deleterious. You pointed to Kondrashov, his quote, contamination of the human genome by thousands of deleterious mutations. You know, why are we not extinct 100 times over? And so you pointed out, and I love this quote here from famous evolutionary population geneticists Keatley and Michael Lynch on the screen. And they point out, and they're not even creationists, Dr. Bergman, they point out that the vast majority of mutations are deleterious. And so we would need some kind of counterbalancing with these beneficial mutations. And as you're pointing out, you would need tens of thousands of truly beneficial mutations to counterbalance this damage.
Okay.
So my question to you then is, the evolutionists will say, okay, well, maybe the majority of mutations are deleterious and maybe there is no counterbalance taking place, but we have natural selection. And so as deleterious mutations accumulate, natural selection will remove those mutants from the population and therefore preserve the organism's health. What's a good response to that?
Well, the problem is they believe in evolution, and therefore I found, unfortunately, no matter how much evidence you have against their worldview, no matter how much evidence you pile up, they believe it, and therefore it's very hard to overcome beliefs. People believe all kinds of foolish things, and it's hard to overcome those. And that's what we're trying to do by facts, but so many of us have found that facts really don't affect very much. Like I did a presentation at Indiana Wesleyan University, and I had clear evidence that mutations are never going to get what they want, and they listened to it and they had no objections to it, but went right on teaching evolution to their students. And so therefore, and I've experienced this several times, that no matter what the evidence, they are true believers and they're not going to change in what they believe because of what evidence I have. And also the problem is one presentation is not going to change them. What you need is hundreds of presentations, which pretty much says the same thing. And then once you get that, then they realize that you're not going to get evolution by mutations because most are not beneficial. You're, as you say, you're going to go 1 foot forward up the mountain, but 5 feet backward down the mountain. And that is over and over what we see happening. So yeah, it's frustrating, I think. But of course, I shouldn't be too critical because I was the same way. I accepted evolution long after there was overwhelming evidence that I knew against it. And so I was a hard nut to crack in this area. And I had to read and study. And finally it sunk in. And I realized that you're not going to go from molecules to man by accumulation of mutations. But I knew this intellectually a long time ago, but it took a while to sink in, and therefore it took me a while to realize that that's not going to work. Evolution is not going to work. And so that's why in churches, I think one presentation every other year is not going to change most people's mind unless they're already in favor toward our worldview. So what it takes is, as one pastor told me, he says, you need to have a apologetics sermon once every month, at least, to help people understand the evidence.
Amen. Amen. That's why we attempt here to put on several a week, because the unbelievers' eyes, the blinders need to be removed. And so, as you said, I was the same way. I was stubborn coming out of college. I was a stubborn evolutionist, and it took at least a year or more of just going through the arguments, going through the data until it finally sunk in. And then we also know 2 Peter 3 says that in the latter days, there's going to be people that deny the creation, deny the world that then was being overflowed with water perished. And so there's some people, it seems as much, no matter how much evidence you give them, they're just unwilling to see it in the light of creation. So I guess my next question to you, and you touched on this, antibiotic resistance. On the genotype, what's going on with these resistant bacteria that can thrive into the next generation? Is this also an example of the breaking down of pre-existing systems, Jerry?
Yeah, the bacteria in some way becomes damaged, and therefore they say it becomes resistant, and therefore the antibiotics don't work anymore. And there are many other ways, of course, that they become resistant because some bacteria, in order to cause a problem, they have to get into the cell and cause problems in the cell. And there are some antibiotics which prevent them from getting into the bacteria. So there are probably a dozen different major means that antibiotic resistance develops. But all of these are either a defense that's broken down and doesn't work anymore, or there's some other problem that prevents them from working. Most of us are exposed to germs every day, and most of us don't get sick. And so when we do get sick, we get bacteria, which cause a problem, and we end up with getting bacteria-resistant strains as a result of antibiotics. And of course, antibiotics select for those bacteria that are resistant. So we have 1 trillion bacteria, and 99.99% are going to die off. They're selected off. 1 per 1,000 or 10,000 is resistant, and therefore it's going to resist, and therefore it's going to, of course, spread throughout the body. So evolution does work with resistant bacteria. Indeed, they do reproduce enormously as a result of the selection which the antibiotic resistant bacteria causes. So it's bacteria resistant strains survive, and therefore they reproduce and take over. And so the selection works really well there, but not to our benefit. To the bacteria's benefit, yes, but not to our benefit.
Right. So it's another example.
Bacteria's benefit either.
And so even with those examples, you're never going to climb, for the evolutionists, Mount Improbable through mutations that are overall reductive. And so great response. I've got a question here that comes in from Mr. Xavier here. And so thank you for the question. And he says, Dr. Bergman, do you concede that mutations can add a small amount of information in rare circumstances? He says, for example, duplicate. Okay, so we talked about duplication earlier. He says duplication in RNase 1 gene of leaf-eating colobine monkey followed by mutations.
Oh yeah, I'm sure there are many examples. But the problem is, do we have enough examples to produce the evolution that we're talking about? So yeah, there are individual examples of where mutations can cause some beneficial effect. My understanding is even in humans, there are a couple, not many, but a couple that can cause beneficial effects and not cause, as far as we know, any negative effects. So certainly when we talk about enormously complex organisms, and when we talk about lots of potential mutations, yeah, you're going to find a few that are beneficial. It's just like every now and then, most mistakes I've made are not helpful. But I have a friend who made a mistake, and he ended up with, in his checking account, instead of depositing $5, it was $500. Well, he made a mistake, which is beneficial. I've never had an experience. They've always been negative. But on the other hand, I'm sure there are people out there who make mistakes, and as a result, they turn out to be beneficial. They're very rare, but they, of course, do happen. And that's one example that I've heard of. Cases. Now you're supposed to, of course, report that to the bank, and it's even if you make a mistake and it ends up getting through the system, but legally you're supposed to report that and say, "Oh, sorry, I made a mistake. Please." I guess probably the best example is when you're getting change from the grocery store, and they need to give you $11 in change, and they give you $21 or $11 and not $2, and therefore legally you're supposed to say, "Oh, I'm sorry, you made a mistake. You owe me $2 change. You gave me a 20 and a 1. So I need to give you back the 20, and you need to give me another 1. So technically, a mistake is beneficial, but problematic if you accept it.
Right. They're basically fighting a losing battle, because even if you gave them 100 truly beneficial mutations without even examining what's going on a genotypic level, like we've been talking about, it's still never going to counterbalance the damage. The exception to the rule doesn't overturn the rule. Isn't that right, Dr.
Right,
Bergman?
that's true. And we're talking about long-term trends and whether we want to go by mutations. And of course you don't. And that quote you gave me, if you could send me the information in that quote, I've seen it before, but send me the source of that quote. I'd like to look that up, because that would be a good quote to use.
Absolutely. I find it fascinating because the evolutionary community, Jerry, they admit that the vast majority of mutations are deleterious, but they're also now admitting that the mutation rate in humans is really high, 100 new mutations per person per generation. And so does that not put shelf lives on genomes?
Yeah, well, sure, it does. It does, and that's why. And some evolutionists, many actually admit that, and they say evolution is true, but it's going backward. And therefore, we need to deal medically with the causes and the effects of these mutations. And so when I was working in the medical school, we were aware of these mutations that cause problems. And our goal was, yeah, they are adding up and there's a problem. But we have to therefore begin to treat in some way, nutrition changes or whatever, in order to deal with these results of these mutations. So they accept mutation rates increasing, but that means the work we have in the medical school is cut out for us because we have to come up with ways of dealing with these diseases.
Right. And you pointed out in your presentation that not only are these deleterious, not only is the mutation rate high, but these mutations are nearly neutral. And so selection can't even see them and do anything about them.
Right.
They build up unchecked and they
Right.
degenerate. The major problem for evolution. So I'm curious. So I've got a question here. A lot of good questions in the audience today. And again, I appreciate the technical nature of your lecture. I think that is necessary at times when we're countering evolutionist arguments. And so you talked about mutational hotspots closer to the beginning of your presentation and made a lot of great points. Do you believe that the so-called gulo pseudogene, and for the audience, the gulo pseudogene is basically supposedly a vitamin C producing gene that humans have and chimpanzees and other primates that is broken. So a shared mistake, evolutionists will say. Do you believe that that is due to a mutational hotspot, perhaps, Jerry?
That is a good explanation of what could be causing it. Yeah, there's no question. And I think that, I'm not sure, have they looked at that possibility? That would be easy to check. You could just compare the pseudogenes from different animals,
right,
and then determine, indeed, is it the same mutation or similar mutations that cause the problem?
Yeah, I have examined a prominent paper looking at the so-called gulo pseudogene, or just vitamin C producing genes in other creatures that it's also broken in. And it seems to be widespread in the biological world because a lot of creatures get vitamin C from their environment, from their diet. And so that gene is therefore subject to breaking down, and it's not going to be any overall harm to the organism.
Yeah, mutation won't cause the lack of survival of that organism because they get the vitamin C from plants, oranges, and so on. Yeah,
exactly. Okay, so next question. Doki Doki Bible Club has a question, and he says, Jerry, what about single-celled organisms that bunch together or clump together to fend off predators? And then he says, thanks for answering.
Well, that's a good example where organisms can cooperate. In essence, we do the same thing. We don't bunch together physically, but we basically work together. When you're sick, I help take care of you. I give you, funds to help you pay your bills and whatever. And so organisms can do that. Dogs do that. They travel in packs. They support each other. And there's lots of stories on the internet about dogs that did that with their peoples, with rescuing babies or rescuing some person. So yeah, single cell organisms, sure, they can bunch together. And of course, if they bunch together, they're less likely to be killed. Therefore, that will encourage them to bunch together. If they're not, they'll be destroyed, or more likely to be destroyed. So therefore, yeah, bunching together would be one way of survival. So that would just happenstance. You bunch together, you're less likely to be destroyed, and therefore that's I'm not sure if that affects selection at all, but that certainly is one mechanism which allows organisms to survive that normally wouldn't.
Is this similar to what we see when single-celled organisms form a colony to protect against a predator?
Yeah, that'd be a similar, except single-celled organisms don't consciously, there's some friends over there, let's go spend time with them. Right. Just, if they happen to be bunched together for whatever reason, they're more apt to survive, and that, of course, can facilitate their getting through certain situations, which if they didn't bunch together, they wouldn't get through. And so therefore that would just be, but certainly many animals recognize that. They'll, especially dogs, you notice, they'll take care of stray rabbits, and a rabbit will come in, and sometimes when you have a dog that's nursing its pups, you get some other animal, cat or something, and they just accept the cat as part of the dog pattern. And a friend of mine has a big dog and hates cats. There's this cat out in the woods that we would walk that when he'd see this cat, boy, he'd chase it up a tree. Well, the cat didn't have a home, and the family decided to take the cat in and started feeding the cat. And now the cat and the dog are best of friends. And so all of a sudden, this cat that he would chase up the tree, walking in the park, when it's living in the house with the dog, they hang around together. And the cat likes the dog because the cat can stay warm, nestled next to the dog, and the dog likes the cat, I guess, gives some variety in life. So indeed, you have these symbiotic relationships that occur through many reasons. And this would be another example of the bunching together. And they do that. Bacteria do that. You notice they clump together.
Right.
Pretty effectively. So
I've seen evolutionists argue that these single-celled amoeba species, they'll cluster or clump together to fight off a predator in the face of a predator. In the lab, they've observed this, and they've argued that this is an example of multi-cell evolution in action.
well,
Is that the case, Jerry?
yeah, that's the just so story. That's the story where they try to justify their worldview by this individual example, which I'm not too impressed with.
Agreed. So next question comes in from Centurion 737. Question for Dr. Jerry. How long does it take for a mutation to reach fixation or saturation in the germline of humans?
Well, it depends a lot on the mutation. If the mutation is problematic, it may be fixated, if so, for a short time. And the best example, of course, is cancer mutations that cause cancer. And they can saturate the germline, the mutations, quite effectively. But of course, once we're aware of this, and of course the BRCA1, BRCA2 are probably the best examples because causing breast cancer, because you're not aware of the problem until you're already had your kids, your family. And so therefore this can be passed on for generation after generation. And this is one way they discovered it's a germline mutation. But of course, nowadays we can diagnose that if your mother, when she's 45, 50, and so on, has a breast cancer, they can determine whether it was caused by a mutation of that gene, and therefore then you have a certain risk if you're female of having that. Your daughters have a certain risk of having that, and therefore they can detect it. Hopefully, saturation will be less so, and elimination eventually will occur as a result of being aware of it. And so that's so fixation. My guess is you had some fixated for decades ago, and they're still cause a problem.
Is there a waiting time problem for the evolutionary model in terms of fixing or getting these beneficial mutations to be stuck in place since the human and chimpanzee split roughly 6 to 10 million years ago?
Well, probably they can try to estimate waiting time. The problem with evolution is the more problems they find, they just solve those problems by extending the origin of humans and other animals farther back.
Right.
So they find a problem, and then instead of originating 50,000 years ago, well, humans must have evolved 100,000 years ago. And so the solution, so many problems that we discover and that they discover with evolution is solved simply by pushing the date of origin back farther.
Rescue it's ad hoc, basically. After the fact, they're coming up with these stories, as you
rescue theory.
Yeah. Rescue mechanisms for the evolution story. Nick has a question for Jerry. Do you have any information on why animals mutating from cold-blooded to warm blood is impossible?
Except I've done a paper on warm-bloodedness, and my conclusion is it's impossible because warm-bloodedness is very complex, and we're not talking about 1 or 2 or 3 genes. We're talking about whole different systems. And so to go from cold-blooded to warm-blooded is recognized as a problem. And of course, evolution solved that by the rescue method. They just extend back the separation from warm to cold back farther. And so we're talking about I'm not aware of any that, besides long-term, again, they believe it happened, so therefore evolution happened, therefore we're warm-blooded, and therefore it must have occurred a long time ago, and therefore we must have evolved from cold-blooded animals, therefore it happened, but it happened a long time ago, and we're not sure how, but we're still working on it. If you read a lot of literature, you come up with these explanations which are commonly used. Well, We're still working on that. Come on. We recognize the body is very complex, and this change from cold-blooded to warm-blooded, there's a lot of changes that have occurred. Therefore, go way, way back, they must have occurred because we have cold-blooded still around today. We have warm-blooded animals around today. Therefore, it must have evolved. We just have to figure out how. That's their common response.
Right. I've discovered the same thing. Examining their own literature as you have, Dr. Bergman, is you'll find a lot of papers dealing with DNA function or mutation accumulation. And instead of questioning whether or not evolution happened, questioning the bigger picture, we're looking for answers. Maybe we'll get an answer in the future, or maybe this hypothesis or that hypothesis. And creationists like you and I, we're sitting there reading these going, or maybe evolution just didn't happen.
Yeah. Well, that's an unacceptable alternative. So,
right.
Given evolution, A, B, C is okay, but D it's an inappropriate resort because we don't believe that could have happened. Creation could have happened. So
right.
It's an a priori decision.
Right off the bat, they're assuming that separate ancestry is not true, that special creation is not true. And therefore, although we have discrepancies with the data here, there must be a naturalistic way to explain it, even if we don't currently know what that explanation is. And so here's a question from Alec Cox. Thank you, Alec. He says, question for Dr. Jerry. Causes for one blue pigment eye and one brown pigment eye, recessive or dominant struggle in the zygote, ? Did you have any thoughts on that, Jerry?
From my understanding, that what happens is if your normal eye color is brown and you have a mutation in one eye, the color is blue and brown covers it. So you have a mutation in one eye, the brown is not produced, and so it will be blue. And therefore, you'll have one brown and one blue eye. And that's fairly common. You'll notice that when common, it's not, thousands, millions of cases, but I have seen a number of people who've had that. What I noticed is that the blue is light blue. It's not a blue that you and I normally would see. My eyes are blue, and they're from far lighter than in my eye. And so what you see is that the brown covers the blue, therefore it's a brown eye. The iris is brown. And the iris diaphragm is blue, light blue, because that's the natural color of the diaphragm. That's what doesn't cause, it just looks funny. And I remember I was waiting in line for a fair somewhere, and this young black woman behind me turned around and said something, and boy, right away, that light blue eye just stood right out, and the brown eye contrast. And, you try to be polite. I mean, I didn't say anything, of course, but, but I'm sure she's used to it. People look at her, they probably double take 3 times, and I double take 2 times. And she probably said, yeah, that's how people kind of respond. So I'm not worried about it. So I think she asked me something about what was going on, but my focus was on the contrast between the blue and the brown eye. You get that with cats and other animals too. And that's the same cause. You have a mutation. From what I know, it's not a dominant mutation. It's just a mutation that happens in you.
Okay.
So it's locally. It's not. I don't know that it's inherited. It may be, but then again, we tend to do research on diseases that cause problems like death,
right.
And therefore we don't. It's hard to get grants to do research on one case or other cases which you have one blue eye and one brown eye. It's curiosity may cause you to question this, but on the other hand, it's not life-threatening, and it's maybe embarrassing. Oh, you can get contact lenses, by the way, that will cover the blue. So some people nowadays, they resort to that. So they wear one contact lens and then they have 2 brown eyes. And it's cosmetic, and of course although the one that's blue, probably that's more sensitive to light. And therefore they may have to have eyeglass differences.
Right, because blue eyes is essentially a localized mutation.
You have less protection. I have blue eyes, and I've always had a hard time outside.
Right.
I never like to go outside because to me, it's so bright.
Mm-hmm.
Everybody else, it's fine, no problem. But to me, it's really bright. When I was playing baseball in high school, I remember I missed the ball every single time when on the outfield. It's because I look up at the sky and I'm blinded. And kids would say, "Are you blind?" I say, "Yeah, I am." Because in this situation, I look up and on a bright day. Now, if we had a really foggy, cloudy day, it probably wasn't a problem. But most of the days we were outside playing baseball, it was pretty bright. So that was a problem. So brown-eyed people, of course, have less problem with brightness. And they're more apt to enjoy spending time outside, where that affected me because I didn't like to go outside, didn't like to be outside. So therefore, I was in the house reading books and doing things like that. So that forced me to be more scholarly because, well, I couldn't be outside playing baseball with my friends because I would, they pick me for the team, they'd invariably lose. And so I realized that I'm not going to, although I didn't realize it till later on, why I had a hard time and the bright lights because of my blue eyes. And I have fairly light blue eyes, so that's a problem.
And that's another thing we have in common, Dr. Bergman, is I also have blue eyes. And so you took those words right out of my mouth, because I was going to point out that, yes, blue eyes is a mutation that came about after creation. And a lot of people say, well, that's a mutation that's not deleterious in any way. But as you've pointed out, and I've noticed too, is I'm a lot more sensitive to light because of those blue eyes.
Yeah.
And so it's not entirely beneficial, is it? I mean, blue eyes are nice, they look good, but in an underlying way, you've pointed out they cause one with them to be more sensitive to light, which can be a struggle.
Yeah, it can be a problem if you're not comfortable being outside that much.
And so I guess my follow-up question to that is, if we have alleles that we as creationists would say are due to mutations over time since the flood, and so is there a way to determine which alleles are created and which are due to the mutations? I'm assuming, based on what we've talked about here, that if we look to more common alleles where maybe the majority of the population has them, maybe those are created. If we have a localized allele, like with blue eyes, those could be due to mutations after Babel. Any thoughts on that, Jerry?
Yeah, that's a good question. That's hard to figure out because all of us have our ancestors going back 6,000 years. And it'd be nice to go back 6,000 years and bring Adam into the genetics laboratory and say, Adam, let's sit down. Let's do some tests here. Let's find out. The only way of knowing for certain whether we have mutations or changes that changed us compared to Adam was, we could compare Adam with us. And there's a debate about whether I think Adam, since he was a Semite, I think Adam was probably brown skin, brown hair, brown eyes. That's my conclusion. That's a common conclusion. And that's why all these light-skinned, blue-eyed Adams just don't seem to fit the bill. And therefore, brown skin, brown hair, brown so on, fits it because we, from the brown dominant people, we can get the light blue, we can get the darker blue, we can get blonde hair, and so on. So I think that probably the best explanation is he was brown. And Jesus, same thing with Jesus Christ. The conclusion is he was probably not a blue-eyed, blonde-haired guy. He probably was Semites, like most of the people in his area, so he'd fit in. And he probably had brown or black hair and brown skin and so on. And that would make sense because he did fit in. When he came down the street, if he had very light skin and blonde hair and blue eyes, probably they would have said something in the scriptures about how different he looked. But as far as I'm aware, there's no scripture that talks about how different he looked. Because my guess is he blended in right with the Semitic people around him, which had brown hair, brown eyes, and brown skin, which in that part of the country would be helpful to have some pigment to protect your skin from cancer, brown hair to protect your skin, so on, your hair area from cancer, and brown eyes to, of course, protect your body from the bright lights which exist in the Middle East. So I would say that's probably what he was.
And so if Adam was middle brown skin, then on a genetic level, he could have been a mix of DNA letters, capital A, lowercase a, capital B, lowercase b. And so he'd be heterozygous for any of these traits, let's say for skin color. And so correct me if I'm wrong, Jerry, from there, from that starting point, you can get every single shade of skin that we see on the planet today, simply from that pre-existing diversity.
And you can do that with a Punnett square. You can figure out what Adam was and how you get every blend possible, and you can figure that out today.
Right. Great point. I love how powerful the biblical model is, and how all good science, not science fiction like the evolutionists put forth, but good science affirms scripture.
Yeah, it does.
Okay, well, we made it to the end. We got one final question, Jerry. I told you you're a fan favorite, so we always get lots of engagement, positive feedback, that is, when you're on the show. And we're doing this live, so we still do have 60 people in the chat, and I want to let everybody know that we've been going for about an hour and a half. And so if you're just joining us, we're gonna wrap things up very soon. Make sure to go back and watch from the start, because I would say Jerry's presentation on mutations is a must watch. And I really want to encourage people to share this presentation around. It's a very important topic. And so the final question for tonight, Dr. Bergman, Centurion 737, thank you very much. He says, question for Dr. Jerry. The atheists and evolutionists claim that DNA is 80 to 90% junk and non-functional. How much of our DNA is actually functional and not junk?
Well, when Jerry the atheist would have probably sided with the common belief, which a high percent of the DNA is junk. That would fit in with evolution. But now we know, if you look at the research, that indeed very little of it, my feeling is almost none of it's junk. Some probably would be, but very little of it is junk. And that reason we know it's not junk is because they found it has functions. Now, a lot of it does not produce genes and thus proteins, but a lot of it's regulatory. And so the regulatory DNA is what they thought was junk because it doesn't produce proteins. And now that we know that the vast majority of DNA is regulatory, we know therefore that it has a function. And you know that because when you have mutations in this DNA, you end up with disease or problems. And therefore you know it must have a function. And therefore we know that since a lot of this does have a function, there are other studies they do which try to determine if it has a function. But in the olden days, the determination was, does it produce protein? If it does, it's useful. It doesn't, it's junk. And that is very naive, and that has been clearly refuted many, many years ago. So the vast majority, probably not all of it's perfect, because we have accumulation of mutations since Adam and Eve. So there's some junk. There's some that is not useful. But on the other hand, I think that the level is fairly low. But what that number is, I don't know. Probably evolutionists, it's said, if you know a little bit about science, you become an evolutionist. If you know a lot about science, you're far more become a creationist, because you realize when you study, for example, the DNA, that the vast majority is useful. Therefore, that is what the creator position implies. And therefore, a lot of knowledge about evolution, and you're less likely to accept it because you realize the problems with evolution.
Right, great points. Junk DNA is junk science, as you've pointed out, just because of 6,000 years of deleterious mutation accumulation and genetic entropy. There might be some junk, but not nearly as much junk as the evolutionary community would say there is. Now, I found that the evolutionists, even though the data, as you've pointed out, suggests that most of the genome is functional, especially those non-coding regions in our genome are acting in as regulatory elements. And so, and they're controlling the protein coding genes of the genome. But they understand that based on what we've talked about, Jerry, deleterious mutation accumulation, if they admit that the majority of the genome is junk, that means they have to admit that the majority of those mutations are hitting functional regions, which degrades genomes and is a major challenge to evolution.
Yeah, that's true.
Have you found that a lot of your non-coding regions of the genome, Jerry, like your long non-coding RNAs, that they tend to be more organism specific, as they're acting as basically genes providing the metadata for the actual building blocks, which are the protein coding genes, in order to function properly?
Well, yeah, they found that a lot of this is, you might call it metadata, but a lot of it is when you have a book, you have words on the book. Well, you have a lot of space, empty space. It has no function except so the words don't go to the end of the page. And so the words don't go into the binding. And so you have a lot of basically paper that has to protect the words or at least highlight the words. And I think the same is true in DNA. You have a lot of DNA that's there in order to protect or separate or organize the actual codes. And so therefore, in doing the research at the medical school, we discovered a lot of the DNA you could just remove and has no effect on the organism. And a lot of that we found does have an effect, but it's a spacing effect, a regulatory effect. When you have genes that are too close to each other, you sometimes have mistakes. So the genes in between, the DNA letters in between, separates the two, and that makes it more effective for the coding and so on. That's what's done with the DNA. Just like you have in a page in a book, you have white paper all around. And if you have too little white paper, it can be hard to read, especially if you have too little paper at the binding. You got to try to move the book open so you could read the letters that go too close to the binding. I've always found that irritating when I make a copy of a page. You need to have a fairly wide white space between the binding and the print. And
right.
So therefore, the same thing with the DNA. You need to have certain spaces in there for various reasons. And those spaces, they don't serve no function, but they don't serve a coding function.
That's a great point. And that speaks to design as well, where you need enough spacing. And that's why a lot of this DNA is involved in chromosomal architecture and organization. And so I guess my follow-up question is, if these protein coding genes acting as the building blocks of the organism, if we understand that they're therefore more similar between creatures, but the non-coding regions of the genome are less or more taxonomically restricted, I guess we could say, why do these evolutionary scientists, when they're comparing, let's say, humans and chimpanzees, they seem to primarily want to focus on that which we've already agreed is more similar, like protein coding regions, and then they ignore your non-protein coding regions?
That has been true in the past, I think, and less true now because they realize the importance of the spaces. But that's true. When you're comparing things, you want to compare things that are comparable. And what's comparable is the genes in humans that produce a heart and the genes in chimps that produce a heart. So many other genes are not comparable, and therefore, why compare them? It's hard to compare things that are not very comparable. And a lot of this spacer gene DNA is that category. It's necessary there, but it doesn't necessarily matter what the letters are, as long as the spaces are there.
Is that DNA also acting as a possible mutational buffer, or just redundant in order, like, so if one gene gets hit with a mutation, but we've got 5 more of that gene basically acting as backup code, wouldn't that be evidence of design?
And that would be, yes, good evidence of design. And that redundancy, when I taught engineering courses, we talk about the safety factor. And you build an elevator, and you want the elevator to hold 10 people. So you build the elevator that works for 10 people. But then you have, the safety factor. And the safety factor is you put as many people in the elevator as you can, and you multiply it by either 3 or 5. And so the safety factor is either 3 or 5. And that's pretty well, that's a policy in all building. When you're elevators, bridges, buildings, and so on, you want to build the building in such a way to where it'll hold well beyond what it could ever be expected to carry.
That right there is an excellent point. The concept of over design. So if you want an elevator to hold 5 people, you're not going to build it to just hold 5 people. You're going to build it to hold way more than that, for safety reasons, as you're saying. So great points, Dr. Bergman. I always have a great time with you. Your presentations are always a must watch. And I really appreciate the work that you put into these. But also, Jerry, I understand how busy you are. So I do want to thank you for the time that you give us for these programs. We always go between 90 minutes and 2 hours. And I always enjoy re-listening to these after, because there's so many good points. So Jerry, I want to hand it to you if you had any final words or final thoughts. And again, thanks so much for tonight's show.
Okay, send me the email about that reference you quoted. And also send me an email so I can access I'm having some computer problems, so I can access my podcast later on this evening.
Sure. Yeah. I'll send you the link to the podcast, and also I will send you some links to these papers that talk about genetic mutation accumulation. So with that, Jerry, again, thank you for your time. To the audience, thank you for tuning in. I see people still making their way in and asking questions. We will have Dr. Bergman on again. And so we do these live. And if you have questions, save it for then. and we'll have another good program. So again, Dr. Jerry, thanks for joining us. To the audience, thanks for tuning in. God bless, and Standing for Truth is out.